Now that you've mastered naming binary molecular compounds, let's take a look at binary compounds that contain what we're going to refer to as type 1 metals. Now, metals come from the left-hand side of your periodic table, the left and the middle, and the bottom of your periodic table. And metals are elements that tend to give up electrons when they form chemical bonds rather than share them. So type 1 metals are metals that form ions with just one oxidation state or charge as an ion. And again, ionic compounds, compounds in which electrons are transferred from cations, which are metals that form positively charged ions, to anions, which are nonmetals that form negatively charged ions. These compounds are neutral overall, and that's going to help us as we go to name these and to write formulas for them. It's a really good idea if you have your periodic table out while we go through this podcast. And what we want to look at are which metals qualify as type 1 metals. Again, type 1 metals being metals that when they form ions have just one possible charge or oxidation state. We're going to use this term oxidation state somewhat loosely here, and we'll develop it further as we go on in the course. But for right now, thinking of charge and oxidation state as the same is going to work for us. So go ahead and do that. And again, we will develop oxidation state itself a little bit more as we go on. These are the metals that are type 1 metals, and it may be a good idea for you to write on your periodic table or somewhere in your notes what type 1 metals are. There are not a lot of them. Most metals do not have just one charge. Most metals form more than one type of ion, and it's very important that you be able to distinguish between them. So on your periodic table, if you look all the way to your left, you have a column that above it will be marked either 1A or 1, depending on your periodic table. And the metals in this column, you need to ignore hydrogen because it's not a metal, but the metals are lithium, sodium, potassium, rubidium, cesium, and francium. Now, right next to that is a group 2A, or group 2, and this contains beryllium, magnesium, calcium, strontium, barium, and radium. Out of group 3A or group 13, depending on how your periodic table is numbered, we have aluminum. And we're going to deal with aluminum exclusively from that group for right now. And then there's a column on the slide called miscellaneous. And this deals with 3 transition metals. And transition metals are the B group metals, depending on your periodic table, or groups 3 through 12 on your periodic table. They're in between the main block elements. And all the transition elements are type 2 metals, meaning they form more than one charge as an ion, except for these 3. Zinc, silver, and cadmium are type 1 metals, and the only type 1 metals out of that big group of transition metals. Now here are the type 1 metals with their charges. If you'll notice, the 1A or group 1 metals, lithium, sodium, potassium, rubidium, cesium, and francium, they all form 1 plus charge ions. Now if you look at these elements, lithium, sodium, potassium, rubidium, cesium, and francium, you'll notice that they have one more electron than the noble gases, which is the group 8A or 18 column of elements that's all the way to the right on the periodic table. Now the noble gases have electron configurations that are very stable. We're going to talk about this a lot more when we get into chemical bonding later in the year. But for right now, if you'll notice that each of these group 1 metals has one more electron than the nearest noble gas, one of the ways that these metals achieve stability when they form chemical bonds is by getting rid of that one electron, and thus taking on the same electron configuration as the nearest noble gas. So you can actually predict what the charge on these ions will be based on the fact that they are just one more electron than the nearest noble gas. They'll lose that and form a 1 plus charge. If you'll notice the group 2A or 2, beryllium, magnesium, calcium, strontium, barium, and radium, these all form 2 plus ions. And they're 2 plus ions because they will give up 2 electrons in order to achieve stability when forming a chemical bond. Now, when an element gives up an electron, normally neutral elements, well, all the time, neutral elements have the same number of protons as electrons. When an atom gives up an electron, it means that it has one more proton than it has electrons, so it'll take on a 1 positive charge for every electron it gives up. So our group 1 elements all gave up 1 electron each, so they become 1 plus in charge. Our group 2 elements, beryllium, magnesium, calcium, strontium, barium, and radium, these will give up 2 electrons, so that their electron configuration can become like that of the nearest noble gas, which is a very stable configuration. So when they give up 2 electrons, it means they have 2 more protons than electrons, and this is what's responsible for the overall 2 plus charge. Now over to aluminum. Aluminum, when it forms an ion, will give up 3 electrons. So instead of having 13 electrons like it has when it's neutral, it now has 10. And if you'll notice, the nearest noble gas also has 10 electrons. Again, the noble gas electron configuration is particularly stable, and it's what these metals try to, what these metals achieve when they form ions. So aluminum is predicted as 3 plus. In that miscellaneous column, the transition metals are harder to predict, and it's best if you just memorize these. For zinc, it forms a 2 plus ion always, and that's the only ion it will form. Silver will form a 1 plus ion, that's the only ion it will form, and cadmium will form a 2 plus ion. You can predict, again, the other metals, the group 1 metals, the group 2 metals, aluminum, but for zinc, silver, and cadmium, it's best to memorize those. It's much more difficult to predict by position. Binary compounds containing type 1 metals require a monoatomic anion. An anion is a negatively charged ion, meaning it's an ion where the atom has acquired an extra electron, maybe 2 electrons or 3 electrons, in order to achieve stability. And again, that stability is achieved when it acquires the same electron configuration as its nearest noble gas. So when combined with these metals, these elements acquire extra electrons from the metals, forming anions. These anions will be given an ID ending to their element names. And you can see examples here. The H- ion is called hydride. The N3- is called nitride. The oxide ion is O2-, and the F- ion is called fluoride. Now take a look at these, because the group 7A or 17 elements we also call halogens, but if you'll notice, each of these have the same charge. Fluoride, chloride, bromide, and iodide ions all have a 1 negative charge, and if you'll notice, they all have, as neutral atoms, 1 less electron than the nearest noble gas. So by gaining 1 electron, they take on the stable electron configuration of the nearest noble gas. And the way that you can predict this charge, for instance, fluorine has, when it's neutral, has 9 protons and 9 electrons. The fluoride ion has 9 protons, which are positively charged, but 10 electrons, which are negatively charged. And the difference between 9 plus and 10 minus is 1 minus, and that's what accounts for its charge. Now oxygen has 8 protons and 8 electrons as a neutral element. When it forms an ion to get like the nearest noble gas, it will acquire 2 electrons. So O2-, it will then have 8 protons and 10 electrons, like that of neon. And so the difference between 8 plus charges and 10 negative charges is 2 minus. And you can predict for that entire group, the oxide, sulfide, and selenide ions are all 2 negative. They need 2 electrons to get like the nearest noble gas. The group 5A or 15 is the nitride and the phosphide ions. Both of those need 3 electrons. Nitrogen needs 3, phosphorus needs 3 to become like the nearest noble gases, which are neon and argon respectively. So when they acquire 3 electrons, they'll have an overall 3 negative charge. And The nice thing about this is you can always predict the charges on these anions when they're combined with metals. So these are utterly predictable and will be of great use when we start combining these ions with type 2 metals, which have more than one possible charge, and you'll see why that is. Here are some basic rules for naming binary compounds containing type 1 metals. The cation, which is the positively charged ion, the type 1 metal, is named first, and then the anion. The cation name is the same as the element name. For instance, K plus is potassium ion. When you name a compound with K plus in it, you'll drop the ion part and then just name the anion afterwards. So the monoatomic anion is given an IDE ending. In the compound name, O2 minus is oxide. So the compound K2O is potassium oxide. Never use prefixes with ionic compounds. I'm going to say that one more time. Never use prefixes with ionic compounds. If the compound contains a metal, run as fast as you can away from prefixes. Here are some examples. For our compound formulas, first we have NaH. This would be sodium hydride. K3N would be potassium nitride. Al2O3 would be aluminum oxide. Ca3P2, calcium phosphide, and AlF3 is aluminum fluoride. Now, here we have an exercise where you're given the compound formula. We'd like you to name the compound. So what I'd like you to do is pause the podcast and write the name of the compound, and then when you're ready, you've gotten all of them written, go ahead and resume the podcast and we'll take a look at the answers. Welcome back. Let's see how you did. BaO, here we have barium oxide. Al2S3 is aluminum sulfide. K3P is potassium phosphide. CaF2 is calcium fluoride. And Li2Se is lithium selenide. How'd you do? Hopefully you did well with that. If not, go back and try those again. Naming compounds given their formula is very important, but so is writing the formula for a binary compound containing a type 1 metal if you're given its name. When we write the formula, here's some things we need to keep in mind. One is that the cations, or the positive ions, and the anions, which are negative ions, must be combined so that there are an equal number of positive and negative charges in the compound. All ionic compounds are neutral. For example, we're going to write the formula for potassium sulfide. We're looking at writing the formula when we're given the name. The name that we've been given is potassium sulfide. So first what we want to do is write the individual cation and anion with their charges. So for the potassium it will be K plus. For the sulfide ion it will be S2 minus. When we look at this, we need to balance the charges. So we need 2 K plus ions to balance the 2 negative charge on the S2 minus anion. So we'll write 2 as a subscript for the potassium in the formula, so the formula will be K2S. Notice that the positive and negative charges are not shown in the compound formula. The compound is neutral because the charges balance. Let's try another problem. Let's look at writing the formula for calcium nitride. The calcium ion is Ca2 plus. The nitride ion is N3 minus. Now this one's a little trickier because we have a 2 plus charge and a 3 negative charges, and we need to get an equal number of plus and minus charges. Now the best way to do this when you have a 2 and a 3 together is to take them both to 6. So 3 Ca2 plus cations are required to balance the charges on 2 and 3 minus. 3 times 2 plus is 6 plus. 2 times 3 negative is 6 negative, so we would then have 6 positive charges and 6 negative charges balancing each other. Now that 3 that we multiplied the 2 plus charges by in the calcium becomes the subscript for the calcium, so it's Ca3, and then the 2 that we multiplied the 3 negative charges by becomes the subscript for the nitride ion. So the formula for this compound is Ca3N2. Let's try writing some formulas. So here we're given the compound name. We want to write the formula of the compound. Now, I'm going to want you to pause the podcast and do this, but remember, for each of these, write the formula for the ion and its charge, determine how many of each ion you would need to balance those charges, and then use that number of how many you need as the subscript in the formula for that particular ion. If you do that, you should do well. So you can pause the podcast now, and when you come back and resume, you'll go right into the slide that has the answers. Welcome back. How'd you do? The first one was potassium bromide. Potassium is 1 plus, the bromide ion is 1 minus, so they go together on a 1-to-1 basis, so it would just be KBr. Now for aluminum nitride, the aluminum is a 3 plus ion, the nitride is a 3 negative ion. Their charges balance 1-to-1, so this again is just AlN. Calcium phosphide, though, calcium is a 2 plus ion. The phosphide is a 3 negative. Here we have that 2 and 3 situation, so we need 3 calciums and 2 phosphides in order to balance those charges. So Ca3P2 is that formula. For lithium selenide, lithium is 1 plus. Selenide is a 2 negative ion, so you would need 2 lithiums to balance that, so the formula is Li2Se. For barium fluoride, barium is 2 plus, each fluoride is 1 negative, so you would need 2 fluorides to balance the 2 plus charge on the barium, so this would be BaF2. And finally, for magnesium chloride, magnesium is a 2 plus ion, the chloride ion is 1 negative, so you would need 2 chloride ions for every magnesium. The formula for magnesium chloride then would be MgCl2. How'd you do? We've come to the end of part 2 of the video podcast series having to do with naming inorganic compounds. I want to leave you with another quote from C.S. Lewis. Courage is not simply one of the virtues, but the form of every virtue at the testing point. Stay tuned for part 3. I wish you well.